Finally, 5.3, binomial distribution. 5.3 can get pretty rough too, but I'm not going to go too deeply into counting techniques, so you won't have to worry too much about permutation and combination. Nonetheless, let me try to explain them as briefly as possible. A permutation is number of different ways to select and arrange k items out of total n choices. We use this kind of formula here. We just multiply, starting from n, the biggest k numbers. Here's an example. Out of a group of 10 finalists, how many different ways are there to select 3 people and award gold, silver, and bronze medals? Well, first place, second place, and third place winners, so we have an arrangement. So this is a combination. Excuse me. This is a permutation, not combination. How many different outcomes are there? We can use this formula. 10 factorial minus 10 minus 3, so 7 factorial, equivalently 10 times 9 times 8. We can do this too. Or even better, you can use your brain. First place winner, how many possible outcomes are there? There are 10 people, so there are 10 possibilities for first place winner. Now for the second place winner, one person is already selected, so there are only 9 people to choose from, so times 9. And then for the third place winner, there are 2 people already selected, so there are only 8 people to choose from. Multiplying them all using the multiplication principle, you get 720. 10 times 9 times 8. That may be a little bit easier way to understand the permutation. First, k number. The biggest k numbers, excuse me. Not first k numbers, excuse me. The biggest k numbers. For example, what if we want to calculate 10 choose 4, for example? Then it will be this. 10 minus 4, so this will be 6 factorial, or equivalently, this times 7, and that's gotta be, well, something. You can use your calculator to figure it out. So the largest 4 numbers multiplied together if it is choosing 4. Okay, so much for permutation, and let's talk about combination. One way to understand combination is to select k items out of total n choices, not minding the order. The second way is we do mind the order, we do arrange, but they're identical, so in the end it doesn't matter. The second idea is more important here for our purpose. And the formula kind of goes like this. N factorial over n minus k factorial is the permutation. After selecting and arranging them, and we have to divide away the number of orders within the selection, and that's how we get this combination, by the way. Here's an example. Out of a group of 10 people, 3 people are to be selected to form a committee. Not the first, second, and third place, but just a committee, trifecta. How many different outcomes are there? This is going to be a combination because we are not minding an order. So let's do that. 10 factorial over 3 factorial times 10 minus 3, which is 7 factorial. More practical computation, 3 highest numbers multiplied over the first 3 numbers multiplied. What if we want to select a committee of 4 people? It's going to be a combination of 10 choose 4. So this is 4 factorial. This is going to be 10 minus 4, so 6 factorial. Practical formula kind of goes like this. 4 highest numbers multiplied over 4 lowest numbers multiplied, and calculated, you're going to get something. This is number of different ways to select 4 people, not 3 people, out of 10 people. Let's go back to this. Now let's consider another aspect of a combination or binomial coefficient, which is identical. The second idea, selecting k identical items. We must arrange 7 S's and 3 Fs. How many different outcomes are there? S for success, 3 for failure. And these are abstract concepts, not Scrabble tiles that you can actually see some difference between, several F tiles and several S tiles. Nothing like those. You have to look at abstract character S and F for success and failure. So even though we are arranging the order, this is a combination. How many outcomes are there? 10, choose 3. Binomial 10, choose 3. For first idea of combination, it is traditional to use C notation for combination. For second idea, even though the eventual number and computation technique will be the same, it is more customary to use binomial 10 choose 3, kind of like this parentheses notation. Of course, the computation is the same, 10 factorial over 3 factorial times 10 minus 3 factorial. The highest 3 numbers multiplied over the lowest 3 numbers multiplied. In the end, you get the same thing. In Mathematica command, we can calculate it as binomial n choose k, kind of like this. Binomial 10 choose 3, binomial 10 choose 4, and binomial 10 choose 5, things like that. I can easily calculate them using Mathematica, but to use handheld calculator, this may be pain in the rear end. Okay, we went through computational techniques and so on. So let's move on to binomial distribution. Let's not worry about counting techniques here. So let's skip this one and let's go over to binomial distribution. Here it is. We begin with something called Bernoulli trial. Bernoulli trial is an experiment with 2 possible outcomes only. S for success, F for failure. Nothing else. For example, if you toss a coin and head is success, tail is failure, then the probability of success is 1/2, and the probability of failure is 1 minus 1/2, so that's also 1/2. And if you repeat that Bernoulli trial a number of times independently, that is called binomial trial. And the probability mass function of the binomial trial is given like this. Binomial n choose k times p to the k power times 1 minus p to the n minus k power. K successes and consequently n minus k failures, but in which order? S, F, SF, SSSF, kind of like this? Well, there are this many different arrangements of S and Fs. That's how we get all these. Now if you want cumulative distribution function, no big deal. We can simply add up the mass functions up to x, so we get something like this with sigma notation. The latter is not that important. Far more practical one is this one. As I said early on, for probability distribution, as far as this course is concerned, I'm using the mass function and the distribution function put together. So we have these two. Let's go over to an example problem. There are 5 red balls, 2 green balls, and 3 blue balls. 20 balls will be selected with replacement. What is the probability to get exactly 5 blue balls? Okay, exactly 5 blue balls. 3 blue balls out of total 10, so the probability P is 3/10, 0.3, but exactly 5 blue balls. So here you have to plug in n equals to 10, k equals to 5. In short, we have something like this. 20 choose 5, 3/10 to the 5th power, 7/10 to the 15th power, 5 successes and 15 failures. This may be rather rough with handheld calculator, but with Mathematica I can get it instantly, kind of like this. Now let's go over to the next problem. At most 5 blue balls, which means 0, 1, 2, 3, 4, or 5 blue balls. How do you get that? Well, we have to calculate them all and add them all up. This is for no blue ball, 1 blue ball, 2 blue balls, 3 blue balls, 4 blue balls, 5 blue balls. Add them all up, you're gonna get, well, 0.41 something. How do we calculate all these? Good luck. Binomial, 20 choose 0, 20 choose 1, 20 choose 2, and so on and so forth. You can do those by, well, this formula here. For n equals to 20, k is going from 0 to 5. And then, well, for success, failure, you can multiply all those and calculate each of those with handheld calculator, add them all up, and you're going to get something like this. Of course, with my mathematical computation, I can get that answer rather instantly. It is time consuming to calculate these, but because binomial is so important, I am going to write these kind of problems in homeworks, exams, and things like those. Exactly why these are important? Well, you don't have to go too far. Just look at the next example. This is a realistic example here. Suppose that approval rate of the current president is 46% and the disapproval rate is 49%. Actually, these are real figures. I looked up from Gallup website on July 27th, 2015 when I wrote this notebook for the first time. Now, let's calculate those probabilities. Out of 18 randomly selected people, what is the probability? At most a third. 1/3 of 18 is what? 6 people. So we are looking at most a third. So 0, 1, 2, 3, 4, 5, or 6 people approves a president. Here we go. 0 success, 0.46 to the 0th power, 1 minus that to the 18th power. So 0 success, 18 failures. 1 success, 17 failures, and so on and so forth. 16 success, 12 failures. They all add up to 18, and then each of them has binomial coefficient. Add them all up, and you're going to get 0.2 something. I can do this rather quickly with my mathematical computation, but if you're using handheld calculator, that could be a bit of a problem. Let's go to the next problem here. I think we have sufficient time for that. More than half of 12 people disapproves the president. So we have to use this one. 49%, 0.49. And then what is half of 12? 6. So more than 1/2. So we have to consider 7, 8, 9, 10, 11, and 12 for p equals to 0.49. Here we go. 7 successes and 5 failures. 8 successes and 4 failures, and so on and so forth, based upon 49%. Calculate them all, we get about 0.36. Yeah, here we go. Now let's go to the final topic. The mean and variance for binomial distribution. Well, please remember this formula. The mean is NP. That's easy to understand. After all, if you roll a die 600 times, expected value is 1/6 times 600. So 100 of the time you can expect an A showing up, give or take. Variance is a little bit harder. Sigma squared is NP1 minus P. Consequently, the standard deviation is the square root of that. Square root of NP1 minus P. And don't ask me why. I can prove it, of course, but I don't think anybody will like it. Just remember these formulae. Mu is NP. Sigma is square root of 1P1 minus P. Or sigma squared is NP1 minus P. Looks like I'm not going to have time to talk about Poisson approximation this time. So let's leave it at that. And that'll conclude chapter 5.